Tonight, we are going to be talking about probability distributions. That's module 2. So I'm Ramya. I am the IT coach at SNHU. I was previously an adjunct professor, and I like to cook and hike and also do some painting. So in tonight's workshop, we are going to become familiar with discrete and continuous random variables. We will look at the Python code for random variables, and then we'll talk about the different distributions, the normal and the t. So a few definitions first. Experiment, it's a procedure that generates an outcome. For example, rolling a six-sided die, drawing from a deck of cards, those are experiments. Outcome is the result of an experiment. That's the number rolled or the card drawn. We have looked at some of these definitions last week, so this is more of a review. Sample space, it's a set of all possible outcomes of an experiment. So if we are rolling a die, the numbers from 1 through 6 would be the sample space. Random variable. A random variable is a rule that assigns a number to every outcome in the sample space of an experiment. For example, if a coin is tossed, a random variable will assign a 1 to heads or 0 to tails. Random variables give numbers to outcomes of random events. And that's why they're called random variables, because they are giving you numbers to outcomes of random events. Now, why are we trying to give numbers to the outcomes? So, for example, when you're rolling, or let's say when you're tossing a coin, we either get a heads or a tails. So we try to quantify the result. We say x is equals 1 when we get head. If it's a tail, then we assign it a value 0. We try to quantify the result. The reason being that it helps with a lot of mathematical computations. For example, we can find the probability. What's the probability of getting a head? What's the probability of getting tails? So in order to do mathematical calculations, it's much easier to work with numbers. So we quantify the results of random events. So the usual numbers are 1 and 0 for tossing a coin. It doesn't have to be this, but we try to do the simplest ones possible. So we assign it a 1 and 0. So there are two types of random variables, the discrete and the continuous. So what is a discrete random variable? It takes on a countable number of distinct values or integers. It's typically counted. For example, the possible outcomes of a die roll, 1, 2, 3, 4, 5, 6. Those are discrete numbers. Those are integers. We can count them. So it's a discrete random variable. On the other hand, a continuous random variable is one that can take any value within a range of values. It includes decimals. It's typically measured. For example, the time taken by a student to complete a timed 60 minutes test. The possible outcomes are in the range 0 through 16, and it can be anything in this range. So it can be 33.6 or 30.2, it can be any number. So this is something that we are measuring. And it includes decimal values. So that's how you remember continuous random variables. They are usually measured and it includes decimals. For discrete random variables, they are usually counted and they are integers. So discrete random variables and their distribution. So before we look at the definition on the top, let's look at the table. and the experiment. So the example experiment is a coin is tossed 4 times. The discrete random variable x is the number of heads. Construct equations and table for PMF of x. So the first part of the table gives the possible outcomes. So when you're tossing a coin 4 times, so if I get 4 tails in a row, so that is T, 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 T. The outcomes are given as T and H. Yes, if you enter your email address in the box on the left, I can send you the recording of this workshop later on. So the first set of, or the first column, I must say, has the possible outcomes. The second column has the value of my random variable x. And the third column has the probability associated with that value. So if I get all tails, my discrete random variable x has a value 0 because I have defined my discrete random variable to be equal to the number of heads. Because I don't have heads, now the value is 0. And the probability is 1 over 16. Why? Because the total number of outcomes here is 16. If you count all the outcomes in every row, it will amount to 16. So the probability of getting 4 tails in a row would be 1 over 16. The second row, I have 1 head and 3 tails. The 1 head can appear in any of the 4 tosses. It can either be in the first or the second or the third or the fourth. And depending on where I get the heads, I have 4 combinations. So my probability here is going to be 4 over 16. And the value of x is 1 because I have 1 head. The third row, I have 2 head and 2 tails. So I have 6 different combinations that can happen. And the discrete random variable is 2, and the probability is going to be 6 over 16. Then can have 3 heads or 4 heads. So this is a table with all the possible outcomes, my random variable x, and the probability associated with it. So any kind of a table like this, where I am mapping my x value, or where I'm mapping my random variable's value with its probability, a table or equation like this, we call that a probability mass function. Now, there is no reason why for some of them I simplified just to show that it can be done, and I left the rest not simplified. So there is no particular reason for having that. So here on the right-hand side, what I did was I did the same thing, the same table, have represented it in the form of equations. So the PMF assigns probabilities to each possible outcome, and the PMF of x is given by P of x equals 0 is 1 over 16. P of x equals 1 is 4 over 16. So here I'm again mapping my random variable's value to the probability associated with it. So for x equals 0, the probability is 1 over 16. So I'm mapping it. I'm writing an equation. I'm saying P of x equals 0 is 1 over 16. So I do the same for all the possible values of x. So equations like this, or anything that represents my random variable mapped to its probability, that is your probability mass function. So it can either be in a form of a table or it can also be as equations. So let's read the definition now on the top. A probability mass function, a PMF, assigns the probability that a discrete random variable x is exactly equal to some value, depicted as a table, a plot, or equation. The notation P of x equals x or P of x is typically used for the PMF of x. And the important thing that you want to remember here is that PMF is always positive. It's between 0 and 1. And the sum of all PMFs is 1. So if you add up all the probabilities in the third column, the value would be 1. Does anybody have any questions before I move on to the probability, the cumulative distribution function? All right. For those of you who joined us late, please enter your email address on the bottom left box. I will send you the recording of this workshop. All right, cumulative distribution function. Again, let's look at the example before we read the definition. What is the probability of rolling a die and it landing on anything less than or equal to 3? So we know there are 3 possible values, 1, 2, or 3. So this probability is the sum of the probability of each event. So here I'm trying to find the probability of getting a value less than or equal to 3. So because I have 3 values, I have 3 probabilities associated with the values. So I have P of x less than or equal to 3 equals P of x equals 1 plus P of x equals 2 plus P of x equals 3. And in the table, we have the random variable x, and I also have the probability P of x. So if I want to find the probability of getting a value less than or equal to 3, I want to add up the first 3 values in my second column. So I do 1 over 6 plus 1 over 6 plus 1 over 6. So if you add it up as a fraction, you will get a whole number. But if I convert it to a decimal, my value would be a decimal value. So P of x less than or equal to 3 is 0.5. Any questions? No, you don't have to. I just wanted to give you the option that if you want, you can always convert it to decimal, because some problems we will be dealing with decimal numbers and some we won't. Yes, please, if you have a question. Right. Are you all set? So for you will notice that if you have already read Zyberg's, that we will be doing the similar functions for discrete random variables and for continuous random variables. The idea would be the same. You have one where you're finding an exact probability and the other one where you're finding the probability of getting a value less than or equal to a value. So properties of discrete probability distributions, we're going to do the mean now. The mean or expected value mu of a discrete random variable x is the sum of the possible values of x multiplied by the probability of the value. This is a measure of the center of the distribution. The mean is calculated as follows. So we have mu equals E of x equals summation x times P of x. where P of X is the probability associated with X. So let's look at an example. So I have a random variable X and I have three values, 0, 102, and 258. These are random values that I picked. The probability is 0.5, 0.35, and 0.15. So if I multiply the first column with the second, so I have X times P of X, so I get 0, 35.7, and 38.7. So in order to calculate the mean, what I have to do is add up all the values in the third column. And that's what the summation symbol means. That find each X times P of X and then add all of them. So here I have mu equals 0 times 0.5, 102 times 0.35, and 258 times 0.15. So, which is the same as adding up all the values in my third column. To add them up, we get 74.4. So that's the mean. E of X is just a notation for the mean of a discrete random variable. So another word for mean is expected value. So instead of just saying mu equals summation X times P of X, we are also adding E of X because it's just another way of denoting the mean. I'm glad my explanations are helping you. At any time, if you think it's getting confusing, just stop me and feel free to ask me any question. So X is an arbitrary value. In my case, I picked up three values. It doesn't have to be these numbers. It can be anything. For example, I can do, let's say tossing a let's say I'm rolling a die. So I have some values for my discrete random variable X, right? If I take those values, I can multiply it with the corresponding probability and then add up all the probabilities or add up all the products. Then I would get the mean. In my case, I just took some random numbers. I have not taken a particular experiment. These are just random numbers that I picked. But depending upon what your experiment is, if you have some values for discrete random variable and you have the probabilities, you multiply them and then add them up to find the mean. The funny symbol, if you mean the summation sign here, yes, it just means add them up. And you'll come across the symbol quite often. So it's a mathematical symbol for summing it up. Sometimes you might see some values below and above it. So you might have summation I equals 1 to n. So you might have I equals 1 below the summation sign and then n on top. It just means that if I have 5 values, I want to add up from 1 to 5. So instead of saying 1 to 5 or 1 to 10, we generalize it and we say I equals 1 to n. X does represent a random variable, Michael. It is just that the value that I chose for it is completely random. I deliberately picked some large numbers because right after this, we'll be looking at the standard deviation and you will see how tedious it becomes when you are dealing with large numbers. And that's when programming languages like Python really help us. We can do these same calculations in Python with just one line of code. So in order to just bring out that fact, I have used some large values here. Yes, the second column is the probability of getting that number. So just imagine some random experiment that you're doing where you have The value of a random variable is 0, 102, and 258. The probability of getting these values is 0.5, 0.35, and 0.15. Okay. Any other questions? So what is x? Was this the x that you asked me? That's the value of the random variable. All right. Any other questions? Feel free to ask me your questions in the chat box if you have specific questions like these. I really like the fact that all of you are asking me so many questions because that's what I want to do. I really want to help you here. So when you ask me questions, I know which part it is that you're struggling with and which part it is that I need to focus on more. So this is really helping me a lot as well. If you don't want to ask me anything in the chat box here, feel free to schedule a one-on-one appointment with me. We can go over any topics that you would want me to. All right, now let's look at the variance. The variance is a measure of the spread of the distribution. So how far away from the mean are the values? Are they clustered close to the mean or are they really far off? That is your variance. How distributed are the values in my data set? So the formula is sigma squared equals V of x. So this is another notation for the variance. And here again we have the summation. So we have x minus mu squared times V of x. So I have taken the same set of values from the previous slide. So my random variables value is 0, 102, 258. The mean that we calculated was 74.4. So the first step that we have to do from our formula is to find x minus mu. So for each value of x, I'm going to subtract the mean. So I have x minus mu values in my third column. The next column, we are going to square the values. So you can see the values are really becoming large. And here is the probability. Again, from the previous slide, I have the same probability values here. And in my last column, I am multiplying the previous two columns, x minus mu squared times p of x. So now if I have to find the variance, I have to add up all the values in my last column. And when I do that, we get 8090.64. So that's the variance. The standard deviation is just the square root of variance. So it's given by sigma. And the value is 89.95. Okay, my first column has my random variables. So I have it from my previous slide, as I said, completely random. Just imagine an experiment where you have random variables. 0, 102, and 258. And I'm going to take the P of X values as well, 0.5, 0.35, and 0.15. So in my first column, I have my random variables value. The second column, I have mu, which we just calculated in the previous slide, to 74.4. The third column, I'm subtracting the first two columns. So x is 0, mu is 74.4. When I subtract, I get negative 74.4. So again, 102 minus 74.4 is 27.6. So I'm subtracting, I'm doing x minus mu. X minus mu squared. So I'm just squaring up the values in my third column. So squaring 74.4 is 5535.36. P of x is again from a previous slide where we had the probability values. So the probability of getting x equals 0 is 0.5. Probability of getting x to be 102 is 0.35. Probability of getting 258 is 0.15. So here I have my P of x values. It is random. For this particular example, it is random. But if you imagine, let's say you're rolling a die. Each of your probability, the probability of getting any value is going to be 1 over 6. So the probability of getting a 1 is 1 over 6. Probability of getting a 2 is 1 over 6. So there you will know the probability. You will be able to calculate the probability. I didn't want to take any example like that. I wanted to have big numbers. So I chose a random experiment. Just imagine any experiment where you have random values 0, 102, and 258. And the probability of getting these values is 0.5, 0.35, and 0.15. My last column, how I got that, I multiplied the previous two column values. So 5535.36 times 0.5 is 2767.68. So for each row, I have multiplied these two columns to get my last column. And then I'm adding up all the values in my last column to get the variance. This is just an example to show you how you can calculate the variance if you have to ever do it by hand. Fortunately, at least for this course, you don't have to do any mathematical computations like this by hand. You will have Python to help you out. How did I get the 5535.36? I have squared the previous column. Yes, sum of probabilities is always 1. Yeah, the point of this class is to see how helpful Python can be in the field of statistics. And you can see when you do your projects and you're doing your discussion, you will have different scenarios, different fields in everyday life, and you will see how you can apply Python there, how statistics play such an important role. No matter which field you choose, there is a lot of statistics involved. And to do all those huge mathematical computations, nowadays Python and languages like R are very, very useful. Your book does not, I'm not sure if there is an example for variance, but I wanted to give you an example just to show you that this can be done by hand, and when you do it, if you have large numbers, it becomes really very tedious. Yes, don't worry too much about this math. It's just an example. We will focus more on the Python. So here, you're going to be looking at the Python code and how we can do the mean, the variance, and the standard deviation, how we can do them using Python instead of doing all the tables and doing all the math that we just did. So we need, from scipy.stats, we have to import the rv underscore discrete. So we are importing a class from a module. I have x and p. X is an array where I have some values 0, 1, 2, 3, 4, 5, 6. These are more realistic values. So this is a value of of the random variables for a particular experiment. Let's say rolling a die. Not exactly rolling a die because the probability here is different. But imagine an experiment where you have your random variables values to be 0 through 6. P is another array which has all the probability values. I have a variable called discvar, and I'm saying that variable equals rv underscore discrete values equals x comma p. What does this mean? What does this do? This line of code is going to map every x value with its corresponding p value. So you're telling Python I have two arrays, x and p. X is the value of my random variable. P is the probability associated with it. Map the two. So Python will now know that the probability of getting a 0 is 0.1. The probability of getting a 1 is 0.2. Probability of getting a 2 is 0.3, and so on. So it will map every x value with the p value. So that's what is going to happen in this line. And once it is mapped, it's going to be saved as a variable discvar. Yes, it does it in order. It goes from the first to the last and it maps every value to the probability. So now you have print discvar.mean. So when you do that, you can find the mean of your random variable. And then you do discvar.var, you can find the variance. And then discvar.std is for standard deviation. So I'm quickly going to stop sharing and open up Trinket and show you the same code there. We will run it and see. Alright, ignore the first three lines where I've imported some modules. So I imported those, but it's not needed right now. From line number 5 through line number 16 is the code that I just had on the slide. So I have my X array and then the P. Then I have discvar. Then I have print discvar.mean, discvar.variance, and discvar.standard deviation. So I'm going to run that now. And hopefully my Trinket is working tonight. Yes, so the mean is 2.7. The variance is 3.8 and the standard deviation is 1.95. So I'm going to go back to the slides. Attach a label to each outcome. I'm not getting your question right. So scipy.stats is a Python library. It's like a package that you'll have to import. I don't know if you have, let me see, if you have done IT-140, I don't think you had to do any import there. But In Python, if you want to run some calculations, Python by itself will not have all of them. There are some packages and modules that you'll have to import. Only using those we'll be able to run certain commands. So scipy.stats is a module that you have to import for statistical computations. We have other libraries also. Last week we looked at the pandas. We also have the NumPy. You have Matplotlib. There are many such modules that are available, which will not be there in a regular Python package. If you download Python 3 in your computer, you will not have all these things. You will have to go and import these things in order to run these same statistical problems in your own computer. Oh, I like the idea of labeling it, and I'm sorry I didn't do it. So I will keep that in mind as a suggestion for next term. So the first value was the mean. I'm sorry, the first value was the mean, second was the variance, and the third was the standard deviation. Yes, I think they're all free because I have tried a few on PyCharm. I have tried to import and it has worked for me. I've not tried all of them though, but I am thinking that they are free. So the modules that we are importing, those are Python code. But Python 3 by itself will not have all those. If you need it, you will have to import it. So when you, let's say you download Python 3 in your computer, you can do basic things, right? But things like this, calculating the mean, variance, standard deviation, a common man is not going to need this every day in everyday life, right? You can have Python, you can run Python, you can do different things in Python. But these are very specific to a particular course, a particular field of mathematics, where only some people might need it. For codes like this, where only a small population is going to need it and it's very specific to a subject, those have to be imported. For example, there is another module called the math module. So if you want to, let's say, find x raised to a y, if you want to find the power, if you want to find the square root, then you have to import the math module into Python. What it is these are sets of codes in Python that will let you run the Python code in your computer, which you will normally not have if you just download Python 3, because these are very specific to math or very specific to statistics. So am I making sense when I say that I'm importing it? These are sets of code, they are Python code, but they don't normally come in when you just download Python. Similarly, for graphing, you have the Matplotlib. That is for graphing. So that is another module that you have to import. So depending on which field you are working in, there are different packages that you have to import. So you're trying to import them where? Do you have Python in your computer and you're trying to import these? Okay, let me look into that because I did try a few in PyCharm and it worked, but I will look into that. Let's see, I will try it one more time, see if I'm able to import these. Alright, this is a screenshot of what we just saw. Yeah, let me try that out, and next week in the workshop I will let you know if it worked for me and what we could do. Right, continuous probability distributions. I think there is a way you can just add your own code in Jupyter. So if you look at the Jupyter tutorial, I think they do talk about one part where you can actually go write your own code and run it. Yeah, for practice. I remember seeing it. If anybody remembers exactly how to navigate to that part, please let me know. But I'm pretty sure it is there for you to try it out. I just don't remember it on top of my head. All right, continuous probability distributions. So what's a continuous probability distribution? So if you look at the diagram that I have the first diagram, I have a histogram. So I have a bin size which is quite large. By bin size, I mean the width of every bar. But in the next one, you see the bin size is small, so I have more data. So let's say you want to find the temperature, you're calculating the temperature throughout the day. The first graph, I have a bin size which is quite large. So I have fewer data there. And let's say I go on measuring like every minute, let's say every 5 minutes, and then I do every minute, and then I do every second. I'm trying to measure the temperature. So I have a large data set. I have large values there. So now what I do is I reduce my bin size. So I get a histogram where I have many bars which are clustered close together, and the bin size is pretty small. Imagine going on doing this, going on reducing the size of your bin, going on reducing the width of your histogram, such that the bars are so close to each other, it's almost like having just a line. And when I join all of these, I get a smooth curve, which looks like a normal curve. This kind of a graph is called a continuous probability distribution. So I have the same thing written here. So let us consider a histogram representing some data with a few bins. If we make the bin size finer and finer, meanwhile we need more and more data, the histogram will become a smooth curve which will represent the probability distribution for the data. So if you're wondering what a continuous probability distribution is, it is nothing but a normal curve. And imagine having all these histograms clustered inside that, and the width is so small that when you join them, it's like a continuous curve. So the probability density function is denoted by PDF. It describes the relative likelihood of all values for a continuous random variable. So this example is given in Zybergs. So the amount of time it takes to do chores is a random variable x where all values between 1 and 2 are equally likely. The thing you have to remember about continuous probability distributions is that unlike discrete random variables, where I can say the probability of x equals 0, the probability of x equals 1, probability of x equals 2, I can give specific values for x for discrete random variable. For a continuous random variable, we cannot do that. We cannot find the probability associated with an exact value. For example, in the graph here, this graph is showing the probability of completing a chore between 1 and 2 hours. If I have to find what is the probability of completing the chore at exactly 1.5 hours, it is not possible to find that. For continuous random variables, we always give a range. We say, what is the probability of completing the work between 1 and 1.5 hours, or between 1.5 hours and 2 hours. There is always a range that we give. We don't talk about a specific value here. And the way we calculate the probability is we calculate the area under the curve. The mathematical part of it involves integrals, which is not included in your course. So you don't have to worry about how you're calculating the probabilities. But you'll have to know that when I'm calculating the probability, I'm actually looking at an area under the curve. And I'm always talking about a range between a point A and a point B, between 1 and 1.5 hours, things like that. So your probability density function is nothing but calculating the probability for a given range. Similarly, for a cumulative distribution function, here again, you don't have to go into how we are calculating the cumulative distribution function because it involves integrals. But the definition is that you're trying to find the probability of getting a value less or equal to an x value. It's very similar to discrete random variables where we found the cumulative distribution function. If you remember, we say for x less than or equal to 3, we did p of x equals 1 plus 2 plus 3. We added 3 probabilities. The idea is the same, but here when you're calculating the probabilities, we have to use integrals. So we don't have to worry about the calculation part of it, but you just want to understand that the cumulative distribution function is nothing but finding the probability of x being less than or equal to x. So for example, when Casey does homework, the CDF describes the probability of Casey finishing in time less than or equal to any value x, such that the probability x is less than or equal to 1.5. So here I'm saying, what is the probability of finishing the work between 1 and 1.5? And the notation here is capital F of x. So in the graph, if you see, they've given you the value. They say f of x equals x minus 1. That value has been got by using integrals, and we don't have to worry about the math behind it. Any questions? So this module has a lot more material. I'm not sure how much I can cover in the next 10 minutes, but I will do my best. If there is anything we are not able to cover and you think you need help, please schedule a one-on-one appointment with me. I will send you these slides if you want to take a look at it later on. So along with the recording, I will also send you the slides so you can take a look at the remaining slides because I don't think we will get through all of it tonight. So the normal distribution. So whenever you have a bell-shaped curve, we call that a normal curve or a normal distribution. And there is a rule, the empirical rule that we want to remember here. So in our normal curve, the middle value, the center value is the mu, which is the mean of your distribution. So on the right, you can see we have marked mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. So the distance between two lines here is sigma. On the left again, I have mu minus sigma. Sigma is the standard deviation. Then I have mu minus 2 sigma and mu minus 3 sigma. Yes, I hope I can get to the central limit theorem, but let's see how much we can cover in the next few minutes. So what the empirical rule is saying is that 68% of the data will fall within one standard deviation of the mean, which means 68% of the data is going to fall between mu minus sigma and mu plus sigma, and that's denoted by the red line here. So from the mean on either side, if I go up to one standard deviation distance, I have 68% of my data lying in this region. 95% of the data fall within two standard deviations. So that is mu minus 2 sigma to mu plus 2 sigma. So that would include right from mu minus 2 sigma all the way up to mu plus 2 sigma. So 95% of your data is included here. And 99.7% of the data will fall within 3 standard deviations of the mean. So all the way from one end, mu minus 3 sigma to mu plus 3 sigma. We have 99.7% of the values lying in this region. Yes, it includes both sides, all the way from the left to all the way to the right. Yes, the standard deviation, mu is the center part. On one side it's positive. So we move one standard deviation at a time on the positive direction, and the other side is going to be negative. We subtract one standard deviation. Okay, the Z-score. So the Z-score is given by x minus mu over sigma. So x is the value that you have in your graph, any point in your graph. Mu is the mean, and sigma is your standard deviation. So for any value x in your graph, you can find the corresponding z value. Subtract the mean divided by the standard deviation. And this z-score, z value, it tells you how far away from the mean your value is. For example, if the z-score is 1.5, it means that it is 1.5 standard deviations away from the mean. Skew is when your graph is leaning towards one side, when your normal curve is not an exact bell-shaped curve, but it is something where it's not symmetrical. A normal bell-shaped is symmetrical, right? But if imagine your graph to be not symmetrical, let's say it was tilted to, let's say, the left, then we call that skewed. So which means that more values are to the left of the mean than to the right of the mean. So I was trying to draw and it didn't work. 1 second. So if I have a normal curve like this, a skewed one would be something like that, where it's not symmetrical. I can also have a graph that is skewed to the right, so I can have something like that. Z-score is nothing but taking every value from the graph, subtracting the mean, and dividing it by sigma. That's your Z-score. If you take every value from a normal distribution, and convert every value to a z-score. And again, if you plot the graph, the resulting graph is called a standard normal curve. And that's what I have shown in the graph below, the gray one. So imagine taking every value from the top graph, converting every value to its z-score and plotting it in the bottom graph. Your resulting graph, you can see the mean is 0, the standard deviations are 1, 2, and 3 on the right, and negative 1, 2, and 3 on the left. Every value in this graph is a z-score. This kind of a graph is called a standard normal curve. And in order to find the z-score, we need to know the standard deviation. Yes. I'm going to quickly explain, this might take another 5 minutes. I'm going to quickly explain the probability. This is this is an important concept. And I'm hoping if when I complete this, you will be able to apply this to the t-distribution. The t-distribution is not very different from the normal one. There is some difference in the formulas. But if you understand this, you should be able to understand the t-distribution. So I will be going over 9 o'clock, just to let you guys know that I will take another 5 minutes or so. Because I really want to explain this, you are welcome to stay. But if you have entered your email address and you think you want to leave the session, I will send you the recording anyways. So now the next part that you're going to do is you're going to calculate the probability associated with a particular z-score. Let's say I have a z-score of, let's say, negative 2.5. And I'm trying to find the probability of getting a value which is less than this value. So the Python function for that is st.norm.cdf. So st is scipy.stats, which I'm importing as st. And the function is norm.cdf. So norm.cdf will return the probability of z being less than a critical value z. So this function takes on 3 values: the z-score, the mean, and the standard deviation. Let's say I have a z-value of negative 0.25. So I have marked that in the graph below. And I'm trying to find the probability of getting a value which is much less than this value. So in my graph, I'm actually trying to find the probability of getting a value to the left of my z value. So that's the purple shaded part in my graph. When I say I'm trying to find the probability of getting a value less than a z value, I'm actually trying to find the area under the curve. So in other words, I'm finding the area of the purple shaded portion in my graph. And in order to do that, we use the Python function st.norm.cdf. So it takes your z critical value. This is just an example. So as we go through the next few modules, we will get different values for z, and then we'll be finding the probabilities of getting a value less than or greater than that value. So, and for an example, I have taken negative 0.25. The mean is 0 and the standard deviation is 1 because this is a standard normal curve. So when you do st.norm.cdf and give these 3 values, your output will be 0.401. And that's your area of the shaded portion in your graph. It's the probability of finding a value which is less than the current z value that I have, which is negative 0.25 for any experiment. Is that making sense? Okay, great. Similarly, I can find the probability of getting a z value greater than a value that I have. In the next example, the value that I have taken, for example, is 1.5. So in my graph, Because it's a positive number, we have marked 1.5 on the right side of the mean. And when I'm trying to find the probability of getting a value greater than this value, I'm looking at the shaded portion in my graph, which is a purple shaded portion. And we have to find the area of that portion. And that will be the probability of getting a value greater than 1.5. So at this point, the Python function that I want to use is st.norm.sf. If you notice, the only difference here from the previous one, there it was CDF, here it is SF. Then we give the Z-score, the mean, and then the standard deviation. The output is 0.0668, which is the area of the purple region. So these formulas for calculating the probabilities, please make a note of these because we'll be using them in the next few modules. So SF is when you want to find the probability of getting a value greater than some value, and CDF is finding the probability of getting a value less than some value. I am not sure, I think that's a very good question. So SF is all values to the right of a value. CDF is all values to the left of a value because you want to find the probability of getting a value lesser than that value. And as we move left in my graph, the values are going to be decreasing. So think of it as to the right and to the left. So the value that I give in the parentheses for SF, it can be a negative number. It doesn't have to be a positive number. I can still have a negative 0.25 in the parentheses. But in that case, I will be finding the region if I mark, let me see if I can draw it. So if I mark negative 0.25 somewhere here, so if I mark it here, I can still find the area of this region. So remember it as to the right and to the left instead of positive and negative, because you can still have a negative value and find the probability of getting a value greater than that value. Yes. SF is going to the right, which means I'm trying to find the probability of getting a value greater than the value I have. CDF is finding the probability of getting a value less than the value I have. So less than is CDF, greater than is SF. So the same thing applies for t-distributions. Unfortunately, I could not get through that part tonight. And I also have the sampling distribution of sample means. I really wanted to go through this, and I know somebody asked me about central limit theorem. So I don't want to hold you guys for too long. Yeah, I know Ricky wanted me to go over it. I don't mind going for another 5 minutes, but I know for those of you who cannot stay longer, please feel free to quit the session. If anybody wants to stay for another 5 minutes, let me know. If you want me to do the central limit theorem, I can do it now. And I can send the recording to those of you who cannot stay longer. Okay, all right. Sampling distribution of sampling means. Now, what does this mean? If I have a population and I take different samples from this population and I calculate the mean, and then I plot the mean, all the means, if I plot all of them, the resulting curve that I get, I call it the sampling distribution of sampling means. The name is big, but the concept is straightforward, that I have a population, I take different samples from this population, and I calculate the mean of this sample. So imagine taking one sample, calculating the mean, plotting it. Taking another sample, calculating the mean, plotting it. You keep doing that many number of times. The resulting curve that you get is called the sampling distribution of sample means. So for a sampling distribution, the mean of the sampling distribution is always equal to the population mean. So the curve that I have for the sampling distribution of sample means, if the center value is mu, if I were to mark the mu here, this will be equal to the population mean. The standard deviation will be different from the population standard deviation. So the standard deviation now will be given by sigma over square root of n. Anybody has questions? N is the sample size. Okay, the central limit theorem, what does it say? The central limit theorem states that as the sample size drawn from the population with a distribution x becomes larger, the sampling distribution of means approaches that of a normal distribution. And the z-score will be given by this. So what they're trying to say is, let's say I have a population which is shaded in green. You can see that it's a crazy population. It's not a normal distribution. It is some kind of a crazy curve. If I have a population like this, and I take samples from this population, I find the mean of all the samples, and then I plot them to get the sampling distribution of sample means. If my sample size becomes larger and larger, then the resulting curve that I get is a normal curve. So I can start off with a crazy population. If I keep taking many samples from this population, as the sample size goes on increasing, then the curve that I end up with will be a normal curve. So the idea is to start off with a crazy curve and end up with a normal curve that I can use for various mathematical computations. So that's what your central limit theorem is saying. And the z-score now will be different from the z-score that we just looked at before. Earlier it was the mean minus the sample mean minus mu over sigma. Now it's going to be the sample mean minus mu over sigma over square root of n. Yes, so we are converting it to a normal distribution. Yeah, you're right. It's because the samples tend to be approximately similar. You are right in that. So the idea is when you take many samples and then you study all the different samples and you find the mean, you do end up with a curve that is very much like a normal curve. Correct. So you take many samples, and when your sample size goes on increasing, the greater is the size, the better is your curve. In your discussion for this week, you will be working on this and you will see the example that you will be running the code and seeing how the sampling distribution of sample mean creates a curve and how the mean becomes equal to the population mean. So the mean of this curve will be equal to your population's mean. Does anybody have any other questions from central limit theorem? The next part I have is the t-distribution. I will stop here tonight. I don't want to take much more of your time. The t-distribution, if you read through it, the formula is different from the normal distribution, but when you look at the probabilities, the idea is the same. I have it in the slides here. The idea is the same. The Python code will differ slightly, and also the t statistic will be different from the z statistic. For a t distribution, you will be talking about the sample standard deviation instead of the population standard deviation. So in your formula, instead of sigma, you will have S. So if you still have questions, please feel free to schedule a one-on-one appointment with me. So I will stop here tonight. Thank you so much for staying for a bit longer. No problem. You guys have a good night.